It's been a little while since I've done a video on electricity and magnetism, and it's a fun part of physics, and it really gets you using complicated vector calculus formulas. And it's a great way to increase your ability to solve these sorts of complicated integrals in Python. Today we'll look at specifically finding the electric potential of polarized objects in one-dimensional form like a string, two-dimensional form like a surface, or a general three-dimensional object. This video is heavily based on my second year calculus in Python video, so if you haven't checked it out, be sure to check that video out. As always, a reminder to join the Discord server as well. I think we're past 500 people now, and to like and subscribe.
I'm back. Get ready for some more. It's going down. Do the math quick. Python so slick. Algebra on paper, yeah, it's making me sick. I got big boy integrals I'm needing to solve and derive and survive. I'm about to evolve, you know that sympy. Yeah, I've mentioned before. Code it up. Gimme some more. E and M integrals got that polarization. It's the situation. Let me be your revelation, cause I'm so cool. And my music is back. Haters be hating. They don't know jack. Like this formula. Pretty cool, right? Material of dipoles looking so tight.
So there's going to be a lot of vector calculus in Python in this video. So if you haven't seen my second year calculus in Python video, be sure to check that out either before or after this video, because it expands upon these things. But what we're looking at here, of course, is vector integrals, which show up all the time in E&M, and how to carefully do them in something like Python as to make it as easy as possible. So the packages are usual, numpy, scipy. For evaluating the integrals, we'll use scipy's integrate library. We have matplotlib as normal. Sympy is going to be used to set up the integrals, and I'll show you how to set them up in a really convenient way in this video. And then a little bit of plotting stuff as well. So we can go ahead and import these. And so the theme of this video is electric dipoles, or dipole density, and that leads to the concept of polarized objects. So what is an electric dipole? Well, suppose you have a charge positive q and a charge negative q, and they're separated by a distance d. And you bring those charges closer and closer and closer together. So this d is really small. And then you have r prime, which sort of points to the location of the dipole, and r, which is, at this point in space, what is the electric field? So everything is contained in all these variables. The question is, what is the electric potential in space? Well, it turns out that as d gets really, really small, but qd is constant, so q gets a little bit bigger, the electric potential at a point r in space is given by this formula, where phi is the potential. And you have 1 over 4 pi epsilon naught. P dot the separation vector, so r minus r prime points from here to here, because r prime plus r minus r prime gets you r, so that vector is here, this vector. And it's p, which points in this direction, dot this vector here, where P is equal to QD. So that's the dipole moment of a dipole. And so like I say, this charge configuration is called an electric dipole with dipole moment P. Now, when you have a polarized material, it turns out you have a bunch of electric dipoles all sort of close together in space, and they're all really small. So how can we quantify this and, evaluate integrals? So this leads into the concept of polarized objects, where you have a bunch of dipoles all together in space, really, really small dipoles, and they sort of add up together to make one big field. And that's what a polarized object is. So because we have many small dipoles together, it's useful to define this with a density. So what I write is dp, which is the dipole moment, a small dipole moment, is equal to this density, capital P of r prime, that's the location in space, times d tau, where that's either a volume or an area in 2D or like a line in 1D. d tau can be any one of those. And so this just conveniently defines, it says that the dipole moment in an infinitely small point in space is proportional, and this is the proportionality factor, capital P, to whatever the size of that is. So if it's a volume, like a small cube, as it make the cube bigger, there's more dipole. So this tells you about the dipole density. So capital P of r is the dipole density. As this gets bigger, if I look at a small region of space, if P is larger, then I have more dipoles in that small area. And so d tau, which is like, it gives you the spatial element here. It says that the dipole is proportional to something to do with space. Well, that can be in 1, 2, or 3 dimensions. I can have a polarized string with a bunch of little dipoles all located on a string. I could have a polarized surface, or I could have a polarized 3D object. And so d tau will change depending on that. So in 1 dimension, d tau is equal to the absolute value of dr prime here. That gives a small infinitesimal line segment. So if I have a string, it says that the amount of dipole in a small area is proportional to the length, if I look at this formula. In 2 dimensions, my area element on the surface is given by this, where r prime u is the derivative of r prime with respect to u. So there you parameterize your surface using 2 variables, u and v. So this is in 2 dimensions, and then in 3 dimensions, d tau is dv. So that can be in Cartesian coordinates, spherical, cylindrical, whatever is useful there. So there's different ways to specify d tau. And I'll go over 1 and 2 dimensions in this video, and 3 dimensions is easy to sort of, generalize to that case. And so the total potential of everything is given by this formula. All we have to do is we have to sum over all the little dp's. So there's a dp at every point in space. I have to integrate over space and add up all those dp's. So I add up all those dp's, I just substitute p of r d tau in this formula up here, and then I integrate over my entire volume. And that gets me all the dipoles added together to make a single potential. So look at the similarity of this formula to this formula here. The only difference is I replace P by capital P d tau, and then I integrate over whether it be a line, a surface, or a volume. So let's start with a one-dimensional object. And this is really simple. So the shape of my object is specified by r prime, and there's one variable here. It says that if that's what one dimension is, you tell me this one variable, this one dimension, and I'll tell you where you're located on the curve. So in this case, we have a spiraling spring-like thing. It goes like this. It's sort of in the xy plane, it's just a circle, but it increases with z, so it kind of looks like a spiral like this. And it goes from minus pi over 2 to pi over 2. The radius is 2r, where this is capital R here. That's just a reference length that we'll use. The polarization, I'm saying that the polarization is equal to P naught, just some constant, times the absolute value of Z. So as you get higher in Z, the polarization increases on this thing. So the thing kind of goes from negative Z to positive Z, and the polarization increases as you get farther and farther from the origin in the Z direction. The position in space we'll deal with, r is x, y, z, and the volume element, because we're in one dimension, is absolute value of dr prime. Now r prime is specified using t. You can do this for any one-dimensional object analytically. So that's equal to dr prime dt dt. So I just write like that. So that's easier to integrate over. So first, I think it's useful to write everything in terms of the reference length and then make everything dimensionless. So what I'll do is I divide by p naught and I multiply by 4 pi epsilon naught r. And you see that that just takes everything in this formula and turns the right-hand side to something dimensionless here. So I divide by p naught, I multiply by 4 pi epsilon naught r, and then I have these factors of r prime over r and r prime over r. So that's just making everything dimensionless. It keeps the problem dimensionless in terms of the reference length r, because r, remember, 2r is the radius of the helix thing in space. So I divided by r's, so this is dimensionless on the left-hand side. This is also dimensionless on the right-hand side. This is something I focus a lot on in my more basic videos, so I suggest checking those out if you don't know what's going on here. And so now, rather than writing r prime over r and r over r everything, I'm just going to assume that all the length things are divided by capital R, so it keeps things a little bit easier. So let's define everything we need here. So I know that my curve is specified by t, right? I give a value of t and I get a location on the curve. So that's the first symbol I define, and t is real. So x, y, z is the location of where we want the potential. We have some point in space, x, y, z. We want the potential at that location due to this charged polarized object. xp, yp, and zp. These are functions. Notice how I say class equals sympy dot function. That's r prime, and r prime is a function of t. So I'm explicitly saying these are functions of t. Also have px, py, pz. Now these are going to be a function of r prime. Remember that the polarization depends on the location on the thing. It'll become easier as I write everything out and we sort of go through the code. So first we define x prime, y prime, and z prime as a function of one variable t. So I go like this, and I have all my variables, right? I have x, y, and z like this. I can, do operations on them. They're just sympy variables. X prime, y prime, and z prime are functions. So they sort of look like this, and I have to explicitly define them as functions of t here. Remember, t isn't time. T is just a variable that we specify the location of the curve. So I explicitly say, well, xp, which is a function, as I defined up here, is a function of time. Same with y prime and z prime. So these are all now functions of time, and I can look at them. And it explicitly says, okay, zp of time. So when I take derivatives and I do things like that, it's really simple. I also define the polarization. So px, py, pz. Well, pz is just, as I define above, it's just the absolute value of z when I divide by p naught. So this is the normalized polarization. And then I define r prime, and p in terms of everything we've defined so far. So r, which is this vector here, the location in space where we want to find the potential, is just x, y, z. R prime is x prime, y prime, and z prime. P is the vector of the polarization, and then I also define the separation vector. So we can look at these. So here's my r, it's just x, y, z. R prime, this is my curve in space. So I give a value of t, and I go on a different location on that curve in space. My polarization looks like this. Remember, it's normalized by, there's no p naught because I divided it out on the left-hand side of the equation here. So this p is really a dimensionless p. And so 0, 0, absolute value of z, that's what the polarization is. And then our separation vector looks like this. X minus x prime. There's no prime variable when I use sympy, so underscore p means primed. So then this is my separation vector, r minus r prime. And so now we can define the integrand p dot r minus r prime over r minus r prime cubed dr prime dt. And that just comes directly from this formula here. So I just use all the variables I've defined to write this like that. And so I have p dot separation vector, that's this up here, divided by the separation vector's norm, the absolute value, cubed, times the derivative of r prime with t. Now this is what's useful, right? I can actually write this, and it will give me the derivatives like this. So I haven't plugged in explicitly what the curve looks like yet. It's all abstract, but it's nice to be written like this. And so then I can actually look at the integrand, right? And I get something that looks like this. So I need to integrate this over all t. In order to integrate over all t, I need to explicitly define the curve now. So I substitute in some things to this integral. I say, well, x prime is equal to 2 times sympy.cos of 4t. Remember that the formula of the curve is given up here. So once I've written down the integrand now in sympy form, I can substitute in the specific things here. So I substitute in x prime, y prime, and z prime, and I just substitute in the things like they're written above. And now my integrand is this, except now the things are explicitly put in. I also simplify it. So this is what my integrand looks like. It's a function of x, y, z, and t. And I want to turn this into a numerical function that we could integrate over in Python, right? This is a sympy expression. If I want to do any numerical integration, I have to turn this into a Python function. That's what I do here. Underscore f means that it's a Python function, and I use sympy.lambdify to turn it into a function, and the parameters are t, x, y, and z, and I'm turning integrand into a function. So it works like any other function. It takes in 4 variables, t, x, y, and z. I can plug in these variables and I get a number like this. So very simple. And I need to integrate this over all t. And if I look back up to my expression here, t goes from negative pi over 2 to pi over 2. So that's easy enough to do. I integrate from negative pi over 2 to pi over 2 using the quad function of scipy. I give x, y, and z as additional arguments, because remember that the potential is a function of x, y, and z in space. And I take the first argument of this because integrate, of course, returns the value of the integral, but also the error on the integral. So I just want the value of the integral here. So it's a function of x, y, and z. So I pass a specific point in space. It integrates over all of this for specific values of x, y, and z, and it integrates over t. So now we can look at a mesh grid. We can say, well, let's take a bunch of different x, y, and z locations and find the potential at all those different locations. So here I'm going to be at a little square. X and y go from negative 1 to 1. So I have a square in x and y. And I'm just going to set z equal to 0. So this helix sort of spirals up like this. And I'm just looking at the potential sort of in the center of the spiral. I want to see what it looks like there. And of course, you can do more fancy stuff like this. You could find it in 3D. You can use the potential to compute the electric field as well, but I just want to keep it simple. And so I define my mesh grid, and then I vectorize this function. So it automatically loops over the numpy arrays that I give it, which are 2D numpy arrays in this case, since I'm doing a mesh grid. And I vectorize this function. I pass in x and y, and then z is equal to 0. And I get phi sort of in this square region in the center of the helix. And I can plot it using a contour plot. And so here I'm using contours. I give it 15 different levels for a specific color map, and I also label it like this. And the electric field is given by the negative gradient of potential. So I just look, the gradient sort of goes this way, so the negative gradient points this way. And my electric field sort of goes like this. You just sort of go with the contours, and you can sort of in your head see what the electric field is actually doing here rather than plotting it as a vector plot. This is what's really useful about contour plots, by the way. Now we're going to get it a little bit more complicated. We're going to look at 2 dimensions. So now again, assume all dimensions are expressed as ratios of capital R. Like in the previous problem, this is just a reference length. So I'm not writing R over R like I do here all the time. I'm just going to assume that everything in dimensions of length is written in terms of R. So the shape of the object, because I have a 2-dimensional object, it's specified by 2 dimensions, and that's u and v here. You tell me u and v, and I'll tell you any location on a surface in 3-dimensional space. So the curve looks like this: u cos v, u sine v, u squared. Now, this might look familiar. This is a parabola in 3 dimensions, or 2 dimensions, I suppose. So it's like a parabola surface. And so u is the radius and v is the angle theta in the xy plane. And I'm saying that u goes from 0 to 2, since u is the radius, and v goes from 0 to 2 pi. So that's sort of what this surface looks like. Any sort of location in here, it's just a parabola that's kind of cut off at a certain point. The polarization is just given by this function here. It's just e to the negative absolute value x squared. Just something that sort of increases with x. So you see how the geometry is sort of messed up. It's a parabola, but it increases with, or it decreases with x. The position in space, again, x, y, z, that's the location, and the volume element looks like this, where r prime u is the derivative of r prime here with respect to u, which is easy to take. So like before, everything is really similar. I define all my symbols, only instead of t, I have u and v now. And when I define my functions, x prime, y prime, and z prime, they're now functions of both u and v. So I can define these, and I can look at them, and it explicitly defines them as functions of u and v. Then I define the polarization. Again, it's just in z, and it's equal to the exponent negative xp squared. Again, like before, I define r prime, and p in terms of everything else. So r is equal to x, y, z. R prime is x prime, y prime, and z prime. P, the polarization vector, and the separation vector. And so I can look at, for example, r prime here, and you see that everything is a function of both u and v, like that. And even in my separation vector, you can see it explicitly. X minus x prime of uv, y minus y prime of uv, z minus z prime of uv. So you really can think of this as like on the surface, right? At some point on the surface, which is specified by u and v, and then x, y, z is your location in space elsewhere. So now I define the volume element and the integrand. So I need to define d tau. And remember, that's Ru cross Rv normalized. So just to show you what I'm talking about here, this is the derivative of r prime with respect to u. I have to take the cross product of this with the derivative of r prime with respect to v, which looks like this. And that just follows directly from this. And then I take the absolute value of it. So that's what I'm doing here. Then the integrand is equal to p dot sep over sep dot norm cubed times d tau. That's just this formula up here. This times d tau, and I've already found d tau in this case. And so my integrand, when I run this, it looks like this. A very complicated function. Note again that I haven't explicitly put in the form of my surface yet. Everything is still abstract in functions of u and v. And so now I can put in the specific surface. So I substitute in x prime, y prime, and z prime as u cos v, u sine v, and u squared, right? And then I simplify it. And now I look at my integrand as a function of u and v, and it looks like this. So it's simplified quite nicely, actually. And I need to integrate this over all u and v, which was specified above. So now I need to create a numerical function that takes in 5 arguments. U and v specify a unique point on the surface. So it's in 3D, but it's a 2-dimensional surface. So only need 2 parameters, u and v. And x, y, and z specify the location in space that we're trying to find the potential. So we integrate over the surface by integrating over u and v. So it's like before, except with t. I have integrand f, which is my integrand function. It takes in u, v, x, y, and z, which is exactly this here. We're turning in the sympy expression into a numpy or Python function that takes in 5 variables and returns a number. And then my phi here, well, now we have a double integral over u and v. So here's the bounds of v in this case, and here's the bounds of u. If you're not used to quad or double quad, make sure to check out my integration in scipy video. And then the arguments, additional arguments, are x, y, and z, because that's like the specific location in space that we're trying to find the potential. And so I can run this. Now I have my function. So I'm looking over a little grid as well. So x and y go from negative 0.5 to 0.5. And we're at a height of z is equal to 2. So we're sort of above. So our parabola kind of comes like this. And we're looking at a little square sort of in the middle of it. And I make my mesh grid like this. And I vectorize this function phi. I find it for a bunch of different values of x, y, and z. It's constant z. And then a little square in x, y. And I can solve for phi. So that took about a minute, a little bit longer than the one-dimensional case, of course, because we have to solve a double integral, which takes a little bit longer. And I can plot the potential in this square. And so it sort of looks like this. And again, the electric field goes from the negative gradient of potential. So here it gets larger and larger and comes in. So the electric field is sort of pointing this way inwards with a negative gradient. So it's pointing inwards to the center here. So anyways, this video is basically just an application of vector calculus formulas in Python. Again, if you haven't seen my second-year calculus video in Python, check that out. I hope you enjoyed this video. If you did, please be sure to like and subscribe, and I'll see you next time.